Thanks everybody for braving the cold temperatures and getting out here today. Today we're going to talk about the indirect detection of dark matter with gamma rays. This is the first part of our 3-week indirect detection section, which is going to dominate kind of the rest of the Compton lectures this fall. So last week we talked about collider detection in particle accelerators like the LHC. And we talked about direct detection in deep underground experiments. Today, and for the next couple of weeks, we're going to talk about indirect detection, which is the detection of dark matter from dark matter interactions happening in space. So, what is dark matter annihilation? You remember the fake Feynman diagram that we showed last week, and I think the week before that too, which is dark matter interacts in some way with standard model particles, and we need that interaction in the early universe so that we can get the density of dark matter today to be about the same as the density of standard model particles. We talked about production and colliders and direct detection. Now we're going to talk about indirect detection, which is time running this way in our Feynman diagram. 2 dark matter particles come in. They annihilate with each other. They might be, for instance, Majorana particles, like we talked about one very briefly a couple weeks ago, where the particle and the antiparticle are the same, so if 2 of them interact, they can annihilate with each other. Or it might be that there is some sort of dark matter, some sort of anti-dark matter, and if those 2 particles happen to come near each other, they annihilate. If 2 particles happen to come together, they bounce off each other or something like that, and we don't see a signal. So 2 dark matter particles come in, they annihilate, you get standard model particles out. So if there's dark matter annihilation at the early universe, in order to get the density of dark matter correct, that should still continue today at some very reduced rate. Reduced because the weak force has gotten weak. It's hard to excite these heavy particles to do your interaction. But something exciting is that unlike direct detection or accelerator experiments, we know what that cross-section is we're looking for, because we know how much dark matter had to interact at the early universe in order to give us the correct density of dark matter out today. We know how much that annihilation had to happen. If the annihilations happened much faster or much more efficiently in the early universe, the dark matter would have annihilated away. There wouldn't be much today, or you would have ended up with maybe only this much, which isn't enough. If the dark matter hadn't annihilated much in the early universe, you would have too much dark matter today, and more than we observe, more than would cause the universe to enclose back on itself, you would have a problem. There are some complications for that, right? We know what the annihilation rate was in the early universe, and we need to translate that to an annihilation rate that we can observe today. So there's a few features. I'm not going to talk about them in any detail. Well, one I'll mention because it's easy to explain. Maybe that cross-section, how often dark matter particles interact when they get close to each other, depends on the relative velocity of 2 dark matter particles. If that happens, at the early universe, everything is moving very quickly, everything is very hot, the velocity is very high, and dark matter particles annihilate a lot. But today, everything is cooled down, dark matter is not moving very quickly. The interactions might be at a much reduced rate compared to what they were at in the early universe. And in that case, the annihilations that you're looking for would be much rarer, and it would be hard to see. But many models predict this so-called magic number, the thermal relic cross-section, of 3 times 10 to the minus 26 centimeters to the 3rd per second. I'll explain the units in a second, but otherwise that's just a number. What does that mean? So this is, in the early universe, if 2 dark matter particles are passing somewhat near each other, basically how close do they need to get in order to bounce off of each other? Right? Interactions that are really strong, like electromagnetism, the particles can be relatively far away, and they can communicate with each other and have an interaction of some sort, either bounce off or annihilate or something like that. For a weak force, they have to get much closer. The cross-section is smaller. And a cross-section, how close 2 things need to get, can be thought of as a target, an area, centimeters squared. So, you basically imagine one particle still, and you're throwing a bullseye and trying to hit that other particle. That's how many centimeters squared you need to get into. And this is the early universe where everything's moving fast. If we calculate this, everything's moving at the speed of light, which is 3 times 10 to the 10 centimeters per second. So that's where the extra centimeter and the extra second come in. or per second come in. And so that is the cross-section that we look for our annihilations. That's our target. You'll see that come up as a line of where we're trying to search for a lot in plots. So what does dark matter annihilate into? I started with 2 dark matter particles. They annihilate. They produce energy. Where does this energy go? Well, it can go into almost anything. If dark matter is its own antiparticle, we talked about quantum numbers a couple weeks ago. Those are all 0 because everything has a particle and an antiparticle. We started with 0. We have energy, and we can distribute that energy into any set of particles and antiparticles that cancel each other out. So we could have, for instance, a pair of positrons and electrons. If we have one, they cancel out. So we started with 0 quantum numbers. We ended up with 0. We could end up with a pair of quarks and antiquarks, and eventually those will turn into protons and antiprotons. We could end up with neutrinos, and neutrinos might be their own antiparticles. So we produce some neutrinos and antineutrinos. We could produce light. And what we're going to talk about today is the production of light in this annihilation event. So generally, you can't. So let me see. Was this on the last one or? Okay. So one thing I'll say, and I might say it again when the slide comes up, is that you can't have dark matter go directly into light, right? And the reason for that is dark matter is dark. It means it doesn't interact with light. It means that there shouldn't be a Feynman diagram where I start dark matter, and end photon, photon. Because if I do that, then I have some interaction that should be happening where my dark matter can interact with light. But what can happen is, say I produce some quarks. These quarks produce protons. There's a bunch of energy in those big jets like we saw at the LHC, jets of all sorts of different energy. Some of those are going to produce things that themselves produce light. Most importantly, they'll produce pions, which is a particle we talked about a little bit, very briefly. And pions happen to decay very effectively into light, gamma rays. Why gamma rays? Why am I looking for this really high energy light? Why not look for, light bulb quality, light visual spectrum light? Remember that the WIMP miracle said that I got about the right relic density of dark matter out. I got the density that I saw today. If the dark matter interacts via this weak interaction force, it interacts via something like W and Z bosons, or maybe via the Higgs. And it has a mass that's about 100 GeV, which is about the same mass as all of these force-carrying particles. Well, if that's true, when it annihilates, I have about 100 GeV particles coming and annihilating. And I have about 200 GeV of free energy that can now take any form it wants. And that should be immediately at the end. I can't write. Now I have all this energy, and a fraction of that is going to go into light, basically through these quarks, through pions, and the pions are going to decay in this huge shower, and it's going to produce some light. And that light tends to have a fraction of that total 200 GeV of energy, a few GeV. The actual number that you tend to get out is that the peak of the light production is at about 1/20th of the mass of the dark matter particle. Fun fact. So if I had 100 GeV dark matter particles annihilating into each other, most of my light tends to come out at a few GeV, which is really energetic light. So the light that's coming from our light bulb is at 1 EV. This is at 5 billion EV. So a light particle with an energy 5 billion times as high as what's mostly in this room right now. So we need a specialized instrument to look for this type of light. There's almost no light that's going to come out of this that's 1 EV or in radio or X-rays or something like that. It's going to come out at very high energies from this collision. Okay, so what do I look for now? Well, I want to look for this light, these gamma rays, coming from sources where I think there is dark matter. And dark matter is going to annihilate. I took this picture because it shows a factor that is a quasar and not dark matter. So if I have an annihilation event, I produce some photons or I produce some neutrinos. And they're not charged, and they move very quickly. And they go off into space in a beam that happens to take them to my detector here on Earth, and I can see that beam. Now that's important because if I see a photon coming in this direction, and I somehow knew it was dark matter via magic, then I would say the dark matter annihilated somewhere along here. Like, I don't know how far away it was, but I know it annihilated along this line of sight. What about, say, a dark matter annihilation and it produces electrons or protons? Well, those are charged particles. There's magnetic fields in the galaxy, and charged particles, accelerate and turn through magnetic fields. So a proton that's produced in dark matter annihilation, for instance, starts going this direction towards me, but then it kind of wanders around over here. It bounces off a magnetic field over there. It does this loop-de-loop. There's a roller coaster ride, and then it comes back to my detector eventually. Or, maybe it started going this way, and then it kind of made it back to my detector. It doesn't point back to where the actual event took place, right? So there's two types of searches for dark matter indirectly. This week I'm going to talk about gamma rays. And those point back. They have the special property that they point back to where the actual dark matter annihilation event took place. I can also look for antiparticles, and I'm going to talk about that next week, but I don't have directional information anymore. I lose all that in the way charged particles move through the universe. This is why gamma ray observations are particularly strong, because I know I can look in a given direction, and what I see tells me about the dark matter there. So where should we look for dark matter? Our gamma ray instruments get to point at sources, and we want to look at sources that have a lot of dark matter signal. And there's three targets I'm going to talk about the most. One is galaxy clusters. We talked about these early on. These are the most massive dark matter halos in the galaxy. Our galaxy is about 1 trillion times the mass of the sun. These can be 100 trillion or 1,000 trillion times the mass of the sun. They have many, many galaxies in them. So this is a galaxy cluster here in the center. These are all these different galaxies that belong to the cluster. And there's lots and lots of dark matter there that makes it a good target. There are dwarf galaxies. These are much smaller things, but they're substructures. They're small parts of our own galaxy, parts of the Milky Way. And they have about 1 million, or maybe 1 billion times the mass of the sun in dark matter. So they're much smaller, not 100 trillion, but maybe 1 billion. But they're closer to us. So, a particle that goes off in a random direction is more likely to make it to our telescope. And these are also good targets. Lastly, you could look at the center of our galaxy. Our galaxy is in a halo of about 1 trillion solar masses of dark matter, and it's relatively close to us. It's 25,000 light years to the center of the galaxy, give or take. And that's another target. These are the three that I'll primarily talk about. So to know where to look, which one of these is best, which one is going to give us the best limits, and what those limits are if we find them, we need to know what the actual dark matter density is in all these locations. And for that, we rely on simulations, right? We need to make some structure formation simulation, and I've showed some that explain how structure forms in the universe and how you form big clusters with subhalos of dark matter and sub-subhalos, et cetera, et cetera. Now I want to do a simulation, but I want to zoom in on just, say, our galaxy. And now I can do it with a question?
Yeah. Why would a black hole be a source for us?
So there may be some dark matter surrounding black holes. But so why does most stuff fall into black holes? It's because it gets close to the black hole, and then there's some friction between a bunch of the matter that's surrounding the black hole, right? So you form a disk that has a bunch of gas, say, in it. A gas particle comes in, it bounces off one of those particles and gets sent into the black hole. So you need some kind of frictional thing to lose energy so that particles can fall into black holes effectively. Dark matter can't bounce off of itself effectively. It doesn't do that very often. And so actually dark matter is much less likely to fall into the center of a black hole than kind of regular gas.
I was thinking that the black hole being dark matter. You don't know what dark matter is, so how do you know?
Yeah. That's something that was thought about for years. We had briefly mentioned it a few weeks back. The problem with black holes being the dark matter is that they're heavy. Objects that are behind them, the light gets bent effectively by something that's that massive. So if I look for a star behind my dark matter black hole, I'll look at the star's light being bent in different directions. And I know how much dark matter there is in our galaxy. That means there's lots and lots and lots of these black holes, and I don't see this stellar light being bent.
What about neutron stars?
Almost the same thing. They'll still bend light in a way that's observable. And neutron stars also emit a bunch of light. I can see a lot of them easily. Yeah. So for these simulations, we have, I'll just zoom in on one. So this is the Aquarius simulation of our, it also has music to it that only I can hear. This is the Aquarius simulation starting at the very early universe, so this is at a really high redshift. This is 500 kiloparsecs. We are about 10 kiloparsecs from the center of our galaxy. And you can see the structure slowly forming, first in just these kind of filaments, and the filaments are going to start collapsing into the center and forming something really dense in the center of this mock galaxy.
Is that dark matter density that you were plotting?
Yeah, this is dark matter density that's being plotted. And so each of these simulations is different dark matter particles. But you can't do the, trillion particles that are actually in a real halo. So each one of these particles is a fake particle that's maybe, 100 or maybe 1,000 times the mass of the sun. But we can still see how they interact and form this kind of dense thing at the center. You're now seeing it form. Now we're, I don't know, redshift 4, maybe 12 billion years ago. We're slowly getting towards the present day. So we've gone so far from 13 billion years ago to like 12 billion years ago. Things are going faster. And so what you're seeing is the really bright, dense thing at the center and all of these other substructures around it. This is actually more of a galaxy cluster than our own galaxy. But so there's all these little things. These are like the dwarf galaxies here. The really bright ones are probably other galaxies. And these things are small dwarf galaxies, and that's the bright center of a cluster of a galaxy. So that tells us from the simulation how much dark matter I expect in different directions. It tells me where to look. Yeah?
Is this principle of annihilation, I'm not really clear about it. So you have the accelerator phenomena that you've proved. That's annihilation, right? And you get the shower. And so this dark matter annihilation, is that, that's a theoretical construct, right? Is that the same kind of annihilation?
Sure.
I know you showed
so it's going the opposite direction. So what I do in particle accelerators is I annihilate two standard model particles with each other and produce dark matter. This is time just runs the opposite direction in this diagram. I annihilate two dark matter particles and they produce standard model particles. So it's a fundamental fact in quantum field theory that if I take one of these diagrams, I can let time run in any direction and the answer is the same. So there's a nice time invariance.
So
none of these things depend on which direction I'm going.
So now you're doing an annihilation. I mean, you're observing annihilation naturally.
Yeah, I'm observing, I'm looking for these hints of the annihilating dark matter in the standard model particles they produce. By the way, I should mention, this is why it's called indirect detection, right? In colliders or in direct detection, I'm actually seeing the dark matter particle come into my experiment and bump off something. That's what I'm looking for. I never see the dark matter here in indirect detection. What I see is these standard model particles that are produced, right? And that makes things complicated because I produce a gamma ray and I see a gamma ray, and I don't know if that came from dark matter or did it come from something else like a neutron star or a blazar or something else in the center of the galaxy that produced a gamma ray. So I need to do statistical methods of some sort, and I have to have some knowledge. So this is why things like knowing where the dark matter is going to exist is really important, because I need to be able to say, well, the stuff that looks like this should be dark matter, right? If it looks like this in the sky, it's probably dark matter, it's not something else. So that makes it tricky. So all of these uncertainties, basically, what does dark matter produce? and where is dark matter on the sky, comes up in this insanely nasty equation that you don't need to know, except I've told you what every piece of this equation is. So I have a dark matter particle, and it produces a bunch of gamma rays. And depending on how the dark matter particle, what it annihilates into, does it produce, say, quarks first, or does it produce electrons first, or something like that, tells me the energy and all this stuff, information about the gamma rays that I need to know. And then I need to know where am I looking for dark matter on the sky. And this is something we call the J factor, which is basically I point in any direction on the sky, and I say, how much dark matter annihilation do I expect in that direction if dark matter annihilates in such a way? So ignoring all of the particle physics for a second, let's compare this point in the sky to this point in the sky and say which one has more annihilations, which one should I look at? And that depends on the dark matter density, how much dark matter is along that direction in the sky, and actually the square of that dark matter density. Why do I square it? Well, this is annihilation, so I need two particles to hit each other. And if the density is low, not only are there less particles, but they hit other particles less often because there's less stuff in the sky. So I want really dense regions of sky, not only because there's a lot of dark matter, but also because the dark matter that is there is hitting other stuff more often and producing particles that I want. So what's important here is that I'm looking at the square of the density of dark matter. And I calculate this for different regions in the sky. It turns out that the highest, what we call J factor, this highest square of the dark matter density is in the center of our galaxy. It's probably the second highest is dwarf galaxies, and maybe galaxy clusters. Those big dense clusters of galaxies actually have a smaller J factor because they're farther away, although the J factor can get larger depending on some assumptions about what happens in very low masses. The cool part about dwarf galaxies is that I'm talking about wimps and dwarfs. It's a really sad language that we use. Measuring dark matter is that in the dwarf galaxies, almost all of the mass is in dark matter. So a dwarf galaxy might have 100 million times the mass of the sun in dark matter, and about 300 times the mass of the sun in stars. Okay, so almost everything is dark matter in these dwarf galaxies. And that actually allows me to measure, by looking at the few stars that do exist, how much dark matter there is. So we talked about early on that dark matter, we know it exists. The first reason is because it dominates these rotation curves of stars. So how fast stars are moving tells me that I need dark matter. Well, here it's almost all dark matter. So I go to these dwarf galaxies and I look how fast stars are moving. Here's a bunch of stars in this dwarf. That's Carina, Draco, Fornax. There's a bunch of stars here, and I measure them. Then I measure the velocities of all these stars, and it turns out that they're rotating around dark matter at the center. And I know it has to be dark matter because there's nothing else there. That has to be what's contributing the mass. So dwarf galaxies are actually really nice. They're the one place where I can actually they're the one place where there's a lot of dark matter, and I can actually just measure how much there is and where it is. So they're kind of the primo targets for dark matter indirect detection. I'm going to talk about some gamma ray instruments, and as someone who thinks about things, all sorts of kind of gamma ray astronomy things that aren't just dark matter, I would be remiss if I didn't talk about why these instruments exist, why they're important, for all sorts of reasons. So I'm going to do that too. So there are two main approaches to studying gamma ray astronomy. One is space-based missions. This is the Fermilab telescope, Fermi Large Area Telescope, launched by NASA. And what does the Fermilab do? So it is essentially a particle detector that got thrown into space. So we had those huge ATLAS and CMS detectors. They were like 40 meters by like 40 meters. Huge, 300,000 tons or something like that. You can't put that in space, it turns out, because that's heavy and rockets aren't that big. So it's smaller. This is about a meter by a meter by a meter, but it's the same sort of technology. So it is built by particle physicists. A gamma ray comes into this detector, right? There's a bunch of different silicon strips and layers of tungsten in this detector. The gamma ray produces electrons when it goes through. Those electrons get picked up by all the silicon strips. Here's a better picture of it. Gamma ray comes in, it annihilates, and it produces electrons here. These electrons go through the silicon strips where they get picked up, and you say, hey, there was an electron coming this direction, this direction. You reconstruct that the gamma ray came in from that direction, and then at the end you collect how many electrons there are and what energy they are in what's called this calorimeter, and that tells you the energy of the gamma ray that came in. So this is a picture of the Fermilab over here, before it got launched into space, obviously. And it's the part up here is basically the telescope itself. This is a bunch of different controls and batteries and computers and stuff like that. This telescope was launched on June 11th, 2008 by NASA. It's still running today. When I was gone a couple weeks ago, I was at the Fermilab meeting, which was in Japan this year. And it's part of an international collaboration. So NASA launched the telescope, but there are major players, Japan, Italy, Sweden, I'm going to leave somebody out, France. Telescope's been operating great for more than 6 years now, taking data. And here's the quality of the data that comes out of the Fermi Telescope. First, I'll zoom in. This was 7 years of egret data. This is the whole galaxy. This is how you look at this map. So this is in galactic coordinates. The center of our galaxy is right here. The galactic plane, the plane of the galaxy, is the brightest thing in the sky. And then these are different bright blazars, I think, from extragalactic, bright galaxies here, and other point sources. So this is what 7 years looked like with the old telescope that existed. This is what I believe 3 days looked like with the Fermi Telescope. You can see everything became better measured in terms of angle, which meant things aren't smeared out anymore. This plane looks really sharp and bright. There are way more point sources. There's one here, 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 here. By eye, I can just pick out like 100 of them on this map. It turns out there's now like 3,000 point sources if you don't just look by eye and you actually do statistics. And Fermilab has discovered tons of new things. So I'm going to talk briefly about them here. This isn't interesting for dark matter, but when you fund a very large space mission, you don't do it just to search for one thing, right? And there's a lot of science that goes on, and I think that's worth mentioning. So for looking for pulsars or pulsating neutron stars, there were 7 detected in gamma rays. I pulled this off yesterday. There are now 161 detected by the Fermilab. And for the first time, we're actually finding pulsars in gamma rays before they were ever found in radio, which is how most observations used to happen. So among young pulsars, we now found 40 that were never found in radio until gamma ray observations told us where to look and what to find. And they were usually followed. Some of them were followed up and found in radio. Some of them are never found in radio, which tells us a lot of interesting things. Here are some of the pulsars on the sky. They're circled. I mean, so these are dim point sources. Like this one is a very probably bright point source if you did all the statistics, but you can't see it by eye. And these are millisecond pulsars, so they were found by the Fermilab. And these are pulsars that were found only, basically, by the Fermilab. Not all of them, but some of them are. So, exciting for that science. The Fermi Bubbles were discovered in 2009 or 10. These are giant gamma ray emission bubbles, because they look like bubbles, that are above and below the plane of our galaxy. So here's the galactic plane here, and just by eye, you will see this weird bubble thing. Nobody knew that existed. And above 50 GeV, it's like the brightest thing in the gamma ray sky. I mean, you don't have to do any data analysis. You can just look at this. It's pretty amazing. This got the Bruno Rossi Prize for these 3 people here, Ming Su, Tracy Slater, Doug Finkbeiner, who wrote the original paper on it. And this is actually telling us something really interesting about our galaxy. At some point, something happened in the center of the galaxy, here, that produced these massive gamma ray emission profiles above and below the plane of the galaxy. And no one quite knows exactly what it is yet. There are 2 theories. One is that the black hole at the center of our galaxy swallowed a star. And when it did, it produced a bunch of energy and big jets that went above and below the plane. And all that energy is now producing gamma rays up here. Second is that there was a bunch of star formation activity right in the center of our galaxy. And when there's lots of really, really young stars, they produce really strong winds that push a lot of high energy material out to the top of the galaxy. And people were investigating basically which of these is true. We had a talk just yesterday about the Fermi Bubbles from a member of the Fermi team after they confirmed this discovery a year or two ago. We can look at the background, and this is also interesting for science reasons, right? The brightest thing was that galactic plane. There were a bunch of point sources we saw. Those are all interesting. We have to study what those all are. But also, just every direction we look on the sky, we sometimes see gamma rays. And there's some background of gamma rays that are coming from almost every location on the sky, and are almost constant. Well, what does that tell us? It tells us there's a bunch of other sources out there producing, not enough photons to be a source that we could distinguish from other things, but just like an ensemble of different background sources. And we can measure these, the spectrum of these. So this is in energy. This is in million electron volts, billion electron volts. A billion times the energy of the light in this room is right here. And you get this really nice power law of the stacked spectrum of all these different sources, none of which we can distinguish by their own, look like this. And then they fall off. And this fall off is really interesting. It was predicted for a couple decades. Just this year it was announced that it was observed by the Fermi Telescope. That's exciting. We can also talk about what type of sources make up this background. So we can say, is it made by galaxies that form lots of stars, for instance, star-forming galaxies? Or is it made by dark matter? Is it made by blazars, which are really bright nuclei at the center of galaxies? And it turns out, everyone thought about 5 years ago that it was probably blazars, and it's not. Blazars can't make more than about 30% of this, 21% here, of this total emission for some reasons involving how smooth the emission looks on the sky. That's exciting. Another cool thing that I point out just because it's awesome, we can look back at the Earth with this telescope in space. And this is a fun fact that you don't know, but you can share with your friends later. You look for terrestrial gamma ray flashes. So it turns out lightning is something that everybody experiences and knows about. We don't actually know how a lightning strike starts. And the problem has always been you need to have a really big voltage in the cloud, a sharp voltage drop to get a spark so that that spark can make a plasma in the air, and then the electricity can travel down to the ground or inside the cloud or wherever it goes. And there's nothing inside of a cloud that can produce that voltage drop. It turns out that to have a lightning flash, you need to have a cosmic ray, like a high energy particle coming from space, hit your cloud. And when that hits the cloud, that provides the energy that causes a plasma to form inside the cloud. Once that plasma forms, now you have all the energy in the cloud can travel through that and form a lightning strike. So I think this movie hopefully is illustrated. Maybe, maybe not. Let's skip some stuff. Yeah, so here are different lightning strikes. And every time you get a lightning strike, it's accompanied by a burst of gamma rays from that same cosmic ray that travel up and get detected by our instrument. So we can actually, every time you see lightning strikes, there's gamma rays traveling up. They can get picked up by this telescope. And here where different lightning strikes are happening as they're detected by space, and then also seen on Earth. So if you had no cosmic rays, you would probably have no lightning. That's pretty well confirmed now. Fortunately, or unfortunately, depending on if you've ever been hit by lightning, there are cosmic rays everywhere in space all the time. So there's always the possibility that you can create this flash. So here's the Fermilab detecting gamma rays, and then they say, hey, there was a lightning strike there at exactly the same time. So that's exciting. Cool science. I have a friend who actually, she builds telescopes they put on Predator drones, and they fly them through the lightning storms. It's an unmanned spacecraft, so it's safe, and it flies into these big storms, and it picks up the gamma rays as they leave the storm. Anyway, that's a side story. Another fun way to detect gamma rays are what's called Cherenkov telescopes. So instead of going to space, we're going to stay on Earth. Why? Because it's really a lot easier to build big things on Earth than it is in space. And we now have to look for gamma rays when we're on Earth, and Earth has an atmosphere. And atmospheres are good and bad. They're bad because, well, my gamma ray was coming through the atmosphere, and then it collided with some oxygen or nitrogen or something like that. And it went boom, and I don't have a gamma ray anymore, which is sad, because now I can't detect it down here. But on the other hand, that's a really high energy collision. I had a really energetic piece of light coming in. It hit and blew apart whatever it hit. And that produces a shower, just like a jet in the LHC, of really high energy charged particles that start moving towards Earth. And those particles are moving very fast. They're moving faster than the speed of light in air. So the speed of light is the fastest things can go. The speed of light in a vacuum is the fastest things can go. But light gets slowed down when it's going through objects like the air or like water. That's why if you look kind of through a lake, you can see things bend. It's because light's traveling at different speeds in the water and above the water. Particles that are moving faster produce what's called Cherenkov light. It's this blue glowy light that you've probably seen. It's in pictures. This is a nuclear reactor. It produces lots of Cherenkov light. And it's the same idea as a, what do you call it, a shock. When a jet passes the speed of sound, you get a shock wave. So you have a thing of a charged particle moving really fast, and it hits a bunch of particles, and it's a charged particle moving through, and those particles all want to bounce off the charged particle. But because it's moving faster than the speed of light, they basically don't know that they're supposed to be pushed away until the particle's already gone, right? So the particle's moving at the speed of light, and it hits a particle here, and that particle emits some light, and it produces a particle here, and that particle emits some light. And this light and that light get to this point at about the same time, because everything's traveling the same speed of light. And so you get this really quick blip of really high energy blue light. So you set a bunch of telescopes up on the ground, and a gamma ray comes in, it produces a shower. That shower produces this Cherenkov light, which is at lower energies, and it travels to Earth. And your telescopes look for this Cherenkov light. Now, how bright is this this Cherenkov light? Because it's pretty impressive. These telescopes need to be able to see a light bulb that's 100 miles away. So you put on a 100-watt light bulb, you take a detector, you need to be able to see that light bulb from 100 miles. And what does this Cherenkov shower look like? Here are, so these are the telescopes here. So here's a mock-up of 4 different telescopes. I think this is for the Veritas experiment. Some Cherenkov light hits this telescope coming in this direction here through the telescope, hits this telescope going this direction, this direction, this direction. You reconstruct which angle all these came in, and you say, hey, that's where the shower started. And so in space, you get to reconstruct which direction the shower came in. That's how you know where the gamma ray came from. So there are 2 major operating atmospheric Cherenkov telescopes that work in this way. One is called Heston, and it's stationed in Namibia. And it looks like this. These mirrors, I don't know if there's a person for scale. I'm looking for something for scale in here. I don't know if I see it. Like a car, maybe. Anyway, this is 30 meters tall. It's huge. So it's like a 150-foot thing. Not quite that big. 120-foot thing. This is Veritas, which is in Arizona, and it's its own experiment. Same idea. These are complementary. Hess is in the southern hemisphere. Veritas is in the northern hemisphere. Unlike a space telescope that can go everywhere, these can only look in the hemisphere that they're pointing at. There's also the Cherenkov telescope array, which is currently under development mostly by European countries. If you want to write to your senator, the US is very uncertain whether they're going to contribute any money to this or not, and have been holding out on it for some time. But there will be a Cherenkov telescope array, which is going to be about 10 times larger than either of these. That's going to take this mission to new levels. I'm also going to put down that Andrew McCann, I believe, is going to be your lecturer in the spring. He's there. He works on Veritas and also on CTA, Cherenkov telescope array. And he does a lot of closer observations. He's a real exciting guy, so I think you're in for a treat next term.
Excuse me.
Yeah.
Where's the CTA located?
Funny you should ask. That's under debate. So they're building it but they don't know exactly where they're going to put it. There will be 2 CTAs. One will be in the southern hemisphere, and one will be in the northern hemisphere. They will be built somewhat differently because of the type of science. So the galaxy is mostly observable from the southern hemisphere, like the center of the galaxy. So the southern hemisphere is better for looking at galactic sources, and the northern hemisphere is better for looking at extragalactic sources. So they will probably be built with slightly different configurations to take advantage of the type of stuff they want to look at. For the southern case, Namibia is leading right now, with Chile as another possibility. But I think most people are talking Namibia. In the northern hemisphere, every government is arguing against itself. So I think like just a couple weeks ago, Spain said they toss in another 50 million, but only if it's in Spain. But they don't really have a site that works, but they do have money, you know. So when you get big missions, hopefully everything is done in terms of science, and sometimes there's politics.
You have to tell our legislation that you are looking for God. They will finance it.
Yes. So there's another way to do Cherenkov astronomy. This is called a water Cherenkov telescope. Same idea as before. This produces a big shower, but instead of looking for the Cherenkov light in the atmosphere, I just look for all the particles made in this shower. Hopefully they make it down to my instrument. This is HAWK, which is the new water Cherenkov telescope. It's still being constructed now, although it started taking science data. It's in Mexico. And shower comes down, and these are huge water tanks. Each one is like 40 feet high, maybe like 15 feet around or something. I'm kind of making that up. Well, let's see, are there cars or something? Oh yeah, there's trucks for scale. This is like a bus, I think. They're filled with water. The particle comes in, it produces the Cherenkov light inside your water tank. And then you have a bunch of detectors inside this big tank of water that look for the Cherenkov light inside your detector. Actually, the hardest part is that this is like at 12,000 feet, because I still need the shower to be really bright. I need to be really high up, and I need to lug a lot of water up there. That's
Does
it.
the water have to be some special purity or anything?
It has to be fairly pure, but that's not the major problem. The major problem is you need truckloads and truckloads and truckloads of water at like 14,000 feet. And you have to build all these things. So I think they're actually at the point where they're building one almost every day or every other day. So things are going pretty quickly now. So let's compare these technologies. They're complementary to each other in a lot of different ways. So this is kind of the stats, the breakdown of every single type of experiment. So one thing that you're interested in is the effective area. That's basically how big is this thing, because it can only see a gamma ray, right, if the gamma ray comes through it, or it makes a shower that comes through it, right? So this is the effective part of the sky that basically gets covered, or not the part of the sky, the effective area that a gamma ray comes through, that it would detect it if it went through this kind of area of the Earth. So for Fermi, this is 1 square meter. It's the size of the telescope in space. But ACTs get to look at anything in a lot of atmosphere above it in a lot of different directions. So they have huge effective areas, 100,000 square meters. Which means that if you had a source and you were looking at it with Fermi and an ACT, the ACT will see 100,000 times as many photons as Fermi. That's great. HAWK is about 10,000 square meters. It's not quite as big as the ACTs, but it's closer to that. But you also have a field of view, right? Which is how many directions can I look at with my telescope at the same time? Am I only looking at this little part of the sky, or can I see almost everything? This is where Fermi wins. It can see 6,400 square degrees at a time. That's 1/6 of the sky at all times. And actually, every 3 hours, it sees the entirety of the universe in gamma rays. So, I mean, maybe things are too dim, but it looks at every point in the sky within 3 hours. ACTs only see about 70 square degrees. They're focused in on really small parts of the sky, and if something exciting is happening over here at the same time, they miss it, right? And HAWK is actually another big thing, because any direction that a shower comes in from, it goes through your water tank. And so you can see it from all sorts of directions. So really, if you're thinking how many exciting things do I see, you multiply this effective area by this field of view and things get a little bit closer. What about the angular resolution? This is another important thing for instruments. When a gamma ray comes in, how well do I know what direction it came from? These instruments all work at very different energies, which is something I've kind of mentioned. Fermi works at about a billion times the energy of the light in the room, and at that energy, it can measure which direction the photon came to within about a degree or so, which is a little bit better than the moon in the sky. It's really good for gamma ray astronomy. It's way better than anything else that's ever existed. It's really sad if you compare it to like Hubble or something like that. BCTs are a little bit better. They can measure this incoming gamma ray to about 0.03 degrees, but they're looking at gamma rays that are 1 trillion times the energy of the light in the room, much higher energies. The reason why, you might ask, because gamma rays that have lower energy don't produce big showers in the atmosphere. The showers die off really fast. They don't produce a lot of Cherenkov light, they're too dim to see. So you need really high energy gamma rays. Hawk is actually even higher energy because the shower has to go all the way to the detector down on the ground. But they can see about 0.1 degrees at about 10 trillion times the energy of the light in the room. Lastly, you have a kind of duty cycle, which is how often is this telescope working and taking data. Fermilat's in space and it's always taking data. It just points in different directions and tries not to point at the sun too much. ACTs only work when it's dark because they're looking for this light bulb that's 100 miles away, and if it's sunny outside, that doesn't work so hot. So they only work when it's dark, and actually only when it's about a new moon or vaguely a new moon or not a full moon right above your instrument. So they see about 25% of the time, about 2,000 hours a year they're working with. And Hawk is also 100% because the shower is a charged particle shower that comes through your detector, and the sun doesn't do that. So you compare all these numbers to each other, and you try to figure out which instrument's best, and it really depends on what you're looking at. Yeah.
Optical telescopes can often complement each other. In other words, you see something.
That was my next paragraph.
Oh,
yeah. So these are complementary in a lot of different ways. For instance, let's say something really exciting blows up in space and produces a big gamma ray shower, right? Well, every 3 hours, Fermilat's going to see that thing because it sees the whole sky every 3 hours. So there's a way that the Fermilat says, hey, that's exciting, that looks out of the ordinary. And it sends a message to the ACT guys that says, hey, go point at that, right? Because the ACTs are going to take a lot more data. They're going to get a lot more photons faster. But they might have missed it because it's not in their sky view, unless they happen to be looking at it that day. And they only look at a really small portion of the sky, so that's unlikely. So there's important stuff going on that way. There's another instrument on the Fermilab, actually, which is made to look for gamma ray bursts, which are bright, short bursts of gamma rays. It can see basically the entire sky all the time, everything that the Earth isn't blocking. And if something hits that trigger and tells it, look for gamma rays, and a message is immediately broadcast to basically everybody on Earth, and everything switches basically and starts looking at it. Optical telescopes are interested in gamma ray bursts. High energy telescopes are switching. So there's kind of an enormous computational system in place when you have a bright event that suddenly happens to get all the eyes pointed on it as fast as you can. And so telescopes like the Fermilab that can see a lot of the sky all the time are really important for those sorts of efforts. You'll see astronomers sometimes at like 1 a.m. because you get a phone call because something happened, and they're the person on duty, so you get a trigger like something's happening, start looking at your data now. And that's probably one of the more exciting times in science, but I like sleeping, so I don't actually do that myself. So what are some of the things that ACTs have discovered or contributed to in science? So there are blazars, which are really bright centers of galaxies. So these are black holes we think that are 1 billion times the mass of the sun, much larger than the mass of the black hole in our galaxy. And they're pooling in matter and producing these bright jets of gamma rays. And so, for instance, here's how Hess contributed to science. This was some Fermi observations of a really distant blazar, and it kind of looked like this, and it kind of could have been a spectrum that looked like that and went way up here, and it kind of could have been a spectrum that went like that and way down there. And Hess turned on and it looked at it. Hess collects many, many more photons at higher energies Fermilab just doesn't see any photons up here because it's really small and really high energy photons are rare. And so Fermi can't say anything up here, but Hess does, and it tells you this is the right answer. Great. One thing that's pretty exciting that you can do is you can measure how much light there is just in random spots of our universe. Say the area between galaxies, how bright is it? In light, and this has been important for a lot of different scientific things. There's this many theory predictions and this many observations. And they all agree with each other this beautifully or not beautifully. So one thing you can measure is these really distant blazars. That emission that is shown here falls off because of this extragalactic light. Basically, the light coming through the Earth hits that light, has an interaction, and in the location where there's also particles, and that causes this spectrum to fall down here to low energies. And so that can be measured by looking at a lot of blazars and seeing how the spectrum falls at large energies, and Hess is providing really good measurements on that. And also pulsars, which is, I think, mostly what Andrew McCann will talk about next term. They've detected pulsations in the nearby Crab Nebula. So the Crab is a pulsar. It's 1,000 years away. It's that thing that made that supernova explosion that was observed in like 1100 AD-ish. So it's written in by Chinese scientists mostly around 1100 AD that there was something, this thing in the sky that was brighter than the full moon. It was visible during the day. It was so bright. That was the Crab supernova explosion. We can see the pulsar now that was formed by that supernova explosion. It produces pulses of really high energy gamma rays. And everyone used to think that it only produced gamma rays up to 5 to 10 GeV, you know, about 10 billion times the energy of the light in the room. And it turns out it was recently detected that at energies more than 10 times higher, it's also producing pulsating gamma rays. So that changes our theories of how these sort of systems work. Finally, you can study the Galactic Center with something like an atmospheric Cherenkov telescope. This is what the center of our galaxy looks like in really, really high energy gamma rays. That's the source at the center of the galaxy. And then there's this bright emission along the plane. And one thing that was found by the Hess telescope, like I said, Hess is in the southern hemisphere, so Hess is the one that has to look at the center of our galaxy, which is in the south. And in other energies, like in X-ray energies, you would get these sudden flares where the center of our galaxy got much brighter and dimmer again. Hess doesn't see those at TeV energies, which means that the emission mechanism at, say, 100 billion times the energy of the light in the room is different than the emission mechanism at tens of thousands times the energy in the room. And that tells you that there's some new physics going on in the center of our galaxy. And you can make models of what this sort of gamma ray spectrum for the center of our galaxy is supposed to look like that. To note, this is my paper. This tells us about how protons basically get emitted from the center of our galaxy. So, learning new things every day from all these instruments. Now let's go back to dark matter in the 5 to 10 minutes I have left. And what are some observations that are being done with these instruments? What do they tell us that's interesting? So we can look at dwarf galaxies. We can look at the Fermilab. And this is probably the most constraining measurement to date on how dark matter annihilates in our universe. So here are a bunch of dwarf galaxies. There are 25 of them there. Here's that J factor, how many astrophysical annihilations I expect in each direction based on a certain cross-section or something. And then this is the plot. It was just released 2 weeks ago. It highly depressed me. But this is at different masses of the dark matter particle here. So going from, let's see here, 1 GeV, or a billion electron volts, to 100 billion, a trillion electron volts. Here is that cross-section. I said 3 times 10 to the minus 26 is the magic cross-section. It's right there. And here is the solid line, this blue one that says dark matter doesn't annihilate more often than that. And it tells you that dark matter doesn't annihilate at a thermal cross-section. So they didn't see anything in dwarf galaxies. That's why we set these constraints. It doesn't annihilate more than, say, 1.5 times 10 to the minus 26 at about 10 GeV. So it's gone below this thermal cross-section at any mass for the dark matter that's under about 100 GeV, which is putting tension on those sort of models that would have a light-dark matter particle annihilating to produce quarks and gamma rays that we could see. So we're actually starting to use these observations now. For decades, we've been kind of moving down. We've always been way up here when our theory predictions were way down here. For the first time, the Fermilab is allowing us to actually move past this magic number and start to rule out models that we had theoretically predicted long ago. So it's really exciting. This is probably the biggest result that came out of that meeting in Japan. Was shown there preliminarily. I'm waiting to see the paper, which should come out soon. It's pretty exciting. It's also a little bit depressing because you kind of had hoped they would see something. In fact, a year ago, there was a slight hint that they were seeing something down about here, but it appears that that hint has gone away. Atmospheric Cherenkov telescopes can do the same thing. They look at dwarfs, and they set limits. Now, the limits at really high energy are much weaker. And the reason is, when I showed you this whole thing of how much dark matter annihilation I expect in different directions, it goes as 1 over the mass of the dark matter particle squared. So as the mass gets heavier, the amount of annihilations you get goes down rapidly. And so that means it's not that the atmospheric Cherenkov telescopes are doing bad work, but they're looking at really heavy dark matter masses because they're looking at really high energy light. And so that those really heavy dark matter particles annihilate less. And so if they're annihilating at that magic thermal cross-section, you probably won't see much. So here's an observation by Veritas. Here's kind of that 3 × 10⁻26 magic number. And these are a bunch of models that they wrote down from theory. And here's the sort of stuff they're rolling out right now, which is way above that kind of model expectations. Of course, you can be optimistic. You can make models that get this bright. And that's what people did for years. Because you always want, right, if you're a theorist, you want your model to not be ruled out yet. But you want it to be testable really soon. You don't want to have some model that, like, you'll die before anyone ever determines it in an instrument. So you always want your model to be right there. And theorists are really, really good at putting their models right there. But we're getting close to those most naive models at low energies. So at Fermi, we don't have to do that anymore. We actually need reasons to make the dark matter slightly less bright so that we can stay on that kind of cutting edge. Okay. Well, we can look at galaxy clusters, and it turns out that those constraints aren't quite as strong, so I'm just going to glance through them, because I'm already over time and I want to talk about one other exciting thing. So galaxy clusters, we're rolling out cross-sections of way about up here. The thermal cross-section is vaguely on this plot, it's way down here. Here are all these optimistic models. See, they wrote down all the optimistic ones so they could rule them out. And there are the optimistic ones, they're all down there. And it turns out that we haven't seen any gamma rays from clusters whatsoever. Which is funny because there's a bunch of galaxies, there's a lot of bright stuff in clusters, but no gamma ray emission yet, which is interesting, not something you expected. ACTs can do the same thing, and again, their limits are even weaker. They're way here. Thermal cross-section is not even on this plot, it's like way down there, but nothing. Galactic Center, possibly a signal, and that's going to be the entire topic of the last Compton lecture, because I think that's kind of the most exciting potential signal that exists right now. I say that as one of the authors of the signal. So in a completely self-biased way, I think it's really exciting, and I'm going to subject you to hearing about it. Good. Sometimes nature throws you curveballs, though. You're looking for signals from galaxy clusters or dwarf galaxies, and then you see something you didn't expect. So Christoph Vennegaard, over there, came up with announced a paper in March of 2012 that said that he was observing a line of gamma rays in the Galactic Center. By line, I mean a bunch of gamma rays at the exact same energy. So spectrally, suddenly I had 10, 120 GeV gamma rays. I suddenly had 100, 130 GeV gamma rays, and then 10, 140 GeV gamma rays. It was a huge bump. It wasn't actually near that pronounced. That would be a smoking gun signature for dark matter. You can't do that for astrophysics. Here was that plot I thought I was going to talk about. So dark matter can't annihilate directly into 2 photons, right? Because then it would interact with light. But you can write down diagrams where dark matter goes into something, and that something immediately produces 2 photons like this. It's a more complicated diagram. So dark matter particle comes in, dark matter particle comes in. Say these are both 130 GeV, because that's what Christoph was saying. So there's 260 GeV here. All that comes out is 2 gamma rays. Those gamma rays have to be 130 GeV apiece. They have to be exactly the same energy as the dark matter that came in, because energy has to be conserved at the beginning and the end of this diagram. So you can construct this diagram, and the cost you pay for this in quantum field theory is that every time you have one of these little indices here where something has to interact with something. You pay this cost of having to add an extra value of alpha into how often does this process happen. Happens to be this, happens to be 1 over 137, the fine structure constant. Which means that a diagram that looks like this has two more indices, two more little vertexes right here. It should happen 1 over 137 squared times as often as the diagram where it produces something immediately, like electrons. Good. But I should say only dark matter can do that, because dark matter is 130 GeV, 130 GeV. That's the mass of the particle. And then these have to be 130 GeV. Anything else that's astrophysical accelerates electrons basically through magnetic fields. And those don't produce sharp lines in your photon data, right? It accelerates some to 130 GeV and just about as many to 140, almost as many to 150, et cetera, et cetera. You get smooth things from astrophysics. Dark matter is pretty unique in being able to produce these lines. And everybody got excited. You can see this paper now has 280 citations from other papers over the last 2 years. Probably about 200 of those came in the first year. It was the thing everybody was talking about. And there were two questions. Is this line a real thing? And if you see the line, remember you're supposed to pay this penalty of alpha squared. It's supposed to happen 1 in 10,000 times as much as the actual annihilation to go straight to, say, quarks or something like that. Why are you not seeing the quarks? Or why are you not seeing the gamma rays that came from that thing that happens 10,000 times more often? Why are you only seeing this line? So experimentalists interested in this, theorists interested in this. Theorists write papers faster. 180 of those papers out of 200 are written by theorists, are about question number 2. But, and then the line started turning up in all sorts of places. So there was an analysis by Doug Finkbeiner and Meng Su, the guys who did the Fermi Bubbles, that said, hey, maybe there's actually 2 lines, and they were looking at different sources, gamma ray sources that had been detected, but we didn't know what they were yet. They're called unassociated gamma ray sources. Sometimes you find a gamma ray source and you say, hey, that's right on top of where we know that pulsar is in radio, or you look at a gamma ray source and say there's a blazar that we know about back there, and then you know what it is. Sometimes you look at it and find a gamma ray source and there's absolutely nothing, and when they stacked all those together, they found the 2 lines now, one at 130 GeV and a second one at 110 GeV. Turns out you might predict there to be a second line from a lot of theories, so that was exciting. And these unassociated sources could be dark matter subhalos, all those things. And they're only producing gamma rays, that's why you don't know about them. But then the line was also found in the Earth's limb, which it shouldn't be. And so it was found basically, the instrument can sometimes look at the atmosphere of the Earth, and the atmosphere of the Earth produces a bunch of gamma rays. And the reason it does is cosmic rays come in, they bounce off they interact with the atmosphere of the Earth, produce gamma rays. This is very close, so it's very bright. You see a bunch of them in your instrument. This is all astrophysics, so you shouldn't see any line in the Earth's limb. That was distressing. Oddly, though, the line in the Earth's limb wasn't near big enough to explain it. So, sorry, let me go back. You might say, well, this means there's a systematic. My instrument is just sometimes calculating 120 GeV gamma ray and saying it's 130 GeV. And it's sometimes seeing 140 GeV gamma ray and saying it's 130 GeV. So there's some pile-up. My instrument is miscalculating gamma rays energies in a way that makes a bump where there shouldn't be one. And that's what could happen in the Earth's limb, right? If you're seeing a signal here, and this is just supposed to be a smooth spectrum, and you're seeing a bump, it might tell you something's wrong with your instrument. But that bump wasn't near bright enough to explain the signal we saw in the Galactic Center. Everything was a mess. And then it turns out that the oddest thing that can happen happened, and the line just has slowly gone away over the past 2 years. So the Fermi teams went and looked and saw the line. This is maybe a year after Christoph's paper. And here's the line. It's 130 GeV. Here's the bump. This is what they expected the signal to be. This is what it actually looks like. But now it's about 2 sigma. It's a fluke that's about 2 sigma instead of almost 5 sigma, which is what people were claiming at the beginning. So they did a slightly different method. They see a slightly different result. And also things are disappearing away. The saddest part is, here was the significance of the line as a function of time. This is Christoph's sad plot, I think he calls it. And here's how many months the instrument had been operating. And here was how significant you would have said the gamma ray line was at different times. So it got to 1 sigma, and in about 15 months it got to 2 sigma. And you expect wiggles, because these are just small statistical fluctuations. It jumped up, there must have been a bunch of gamma rays there, got up to like almost 4 sigma, stayed around there for a while, got up to 5 sigma. Christoph wrote his paper when he hit 5 sigma, and then it just kind of went down. And actually this clock continues, it just keeps getting sadder and sadder. It's just slowly going down over time. These green and red lines are projections of what it should have looked like. If it was a real signal, it should keep climbing, and it should kind of be like here. And if it's a fake signal, it should kind of go like that. And it's now squarely, it's passed to this bottom green line, which is your 2 sigma if it was real. And it's just kind of gone. It's very sad. And so that seems to be fading away. In Nagoya, they presented this plot of updated data with a new reanalysis, and now there's really nothing. Where is it? I don't know. It's about hereabouts. Just about a little less than 2 sigma there, I guess, and about 100-something-ish GeV. So things seem to be going away, sadly. And that's an exciting story. It got everyone's attention for a long time, and it should, because that's something that's really an obvious dark matter signal if it's real. But it seems that that has not worked out. So next week, I'm going to talk about doubly indirect searches for dark matter. And the question I'm going to talk about is, what happens when dark matter annihilates, and instead of looking for those gamma rays that are produced right at the annihilation site, you look for, say, electrons or protons that are also produced, and make it to your detector. You don't have the spatial information anymore. That's why it's doubly indirect. But there's a lot of things you can do there, and we can see if we can see those too. And then I think there's a 2-week break after that for Thanksgiving and a workshop thing here. And then on the 13th, there'll be the last lecture, which will be on the Galactic Center itself. So thanks.
If you could get a bunch of dark matter in a can and on your surface, it would be very heavy, right?
It depends on how much you got, yeah. But,
So
yeah.
you were hypothesizing that because of you can't see the gravity effect of this stuff. So is dark matter the mass and gravity the same as visible matter, or could it be something different?
Yeah, so we think the mass it works the same way. And actually, the dark matter mass that's in this room is really, really, really small. I think the dark matter mass that's contained in Earth is a couple of grams throughout the Earth's surface, but it's everywhere through space. It adds up, there's a lot of space. So the dark matter particles I'm talking about are, I said, 100 GeV. So that's 100 times the mass of a single proton. So each dark matter particle itself is still pretty light. If you've got lots and lots of them in a box, they get heavy in the same way as anything else. But the dark matter particle itself, is a particle. So so it's relatively light. There's 10 to the 26, particles kind of in this region right here. And so if there's an extra dark matter particle, it's 1 part in trillion adding to the mass. So it's pretty small. Yes, in the back.
There are no coincidences in physics, and yet you calculated an alpha equal to 1 over 137, and that is the denominator in the fine structure constant.
Oh, that's because alpha is the fine structure constant. That's why. So alpha is the fine structure constant, which is a 1 over 137. Okay. Yeah. Yeah. Every time you have that diagram. Sorry. Yes. So it's not a coincidence. We were talking about the same thing. Yes, that's alpha, that's the fine structure constant, and you pay a cost of the fine structure constant every time you, and that's calculated actually from the probability of these diagrams happening, that's how you get alpha. So, any other questions? Oh.
So you're talking about all these collisions of dark matter particles, and I don't know whether you've addressed this in any way at all, but if gravity is the force that acts on dark matter, is there any thought that this stuff, these particles accumulate like regular matter and form massive entities, for lack of a better term, stars, planets, whatever, that is totally aside from what you're talking about individual particle collisions?
Right, so I mean you have that sort of structure formation that I showed here, right? So dark matter is clumping and it's forming structure. That structure is not near as dense as, say, the air in this room or the ground. And the reason is, to form structure, you have to be able to have particles cool down when they hit each other and be able to clump together, right? So dark matter particles are moving about 300 kilometers per second right now, and the molecules in this room are moving not fast with respect to each other. That means you need a force that slows down particles and gets them to be moving at about the same time. You need a friction force, basically, so that, if I have a dark matter particle running across the table, it slows down, just like this slowed down the table. There's no frictional force for dark matter because the frictional force involves light. So this frictional force is because I have an electromagnetic force in between this and the table. It slows this thing down. So dark matter doesn't get to clump the same way that baryonic particles do because it doesn't have a strong interaction force.
And so is it analogous to a gas then? It stays a gas? It's just like everything's moving so fast?
I mean, gases still get to cool when they hit each other. But like a really, really dilute gas, if there was almost no particles, then there would be very few interactions. So it would behave the same way as a really, really vacuumly diffused gas would tend to behave. Yeah.
You mentioned the gamma ray spectrum, and I wondered with the dark matter, you're dealing, if it interacts, you're dealing with particles. So is there a specific, I mean, the particles will have specific type of spectrum you're looking at, and then gamma rays are interacting with all kinds of stuff. So I just wondered about, like, what is the spectrum that you're interested in?
Let's see if I can find a good. I'm going to pick up one of my own papers just because I know where, not because I did this, I should mention, just because I know where it is in my own paper. Here we go. So here's gamma rays. So on this is the gamma ray spectrum here that you get from different masses of dark matter particles annihilating into different types of things. So here's a 40 GeV dark matter particle. It annihilates into 2 bottom quarks, so 2 heavy quarks. And this is the gamma ray spectrum you get out. So here's the amount of energy at everything. You can ignore this. And this is the energy of the photons that you would observe. So you can see 40 GeV, it peaks here right at about 2 or 3 GeV, what I said before, about 1/20th of the mass. Here's a slightly different dark matter spectrum. It's 200 GeV, but it annihilates into W bosons, W plus and W minus bosons. And then it gets to the spectrum that looks like this. It comes up here mostly just because the dark matter mass is heavier, right? Notice this is 40 GeV. You get nothing above the mass of the dark matter particle. It's the conservation of energy. Same here, it cuts off the mass of the dark matter particle. This is a really hard spectrum that happens if dark matter annihilates into muons. And the reason is muons very quickly produce electrons. It's not far down this jet shape. Muon just produces gamma ray plus electron. You look for that gamma ray. For this paper, it was also important here the electrons and positrons in spectra that get produced in the same sort of annihilations. That's because we were talking about something different. And like I said, I didn't do any of that. It just appears in the paper, and I knew what page it was on. I don't want to take credit for something that I was done 15 years before I started thinking about physics. Yeah. So actually, and the way that you can calculate these, I guess it's worth pointing out. Dark matter comes in, and it does some blobby thing that we don't know. And I said it produces B quarks, right? Well, this dark matter was 40 GeV, 40 GeV. By conservation of energy and momentum, this is 40 GeV, this is 40 GeV. And from the accelerators, I know exactly what a 40 GeV B quark does. Because I haven't found the dark matter, but all that happened is I produced a 40 GeV quark. A 40 GeV quark from particle constraints, which I produce 40G quarks all the time in the LHC, I know exactly what it produces in terms of gamma rays, in terms of protons and antiprotons and electrons. I know what all of those numbers are. So that's why I can exactly calculate what all those spectra are. Yeah. Other questions? Cool. Well, I'll see everybody next week. Have another good talk as we continue to go through this. Thanks.